Hi, my name is Scott. As part of our series of STEM activities that you can try out at home, I wanted to teach you a little bit about optical illusions by talking about Jedi mind tricks. Now, if you haven't seen the Star Wars movies, that's okay. Nothing in this is going to need information from the Star Wars movies. So using this information, we're going to go forward and we're going to start talking about some optical illusions that we can try ourselves, and they're going to basically figure out how humans perceive things and how we can trick that. And once we can figure out how humans perceive, then we can use that information to find shortcuts and tricks, and that's how optical illusions work. They're taking advantages of these cognitive shortcuts that humans use to perceive the world. To start off, we're going to do some word processing illusions. So in a minute, I'm going to flash up a sentence on the screen, and your job is just to read that sentence out as quickly as you possibly can, but we're only going to keep it on the screen for a second. If you didn't get it, that sentence has an error in the title. So if we open it up again, you can see that it says Paris in the spring. You might not have seen the two thes the first time unless you've happened to see this illusion before, but our brains don't process information the same way that something like Microsoft Word or other word processors process letters and words like this. So rather than looking at that first word and saying P-A-R-I-S, Paris, got it, next word, I-N, in, got it, next word, we don't process information like that. The way the human brain would process this would be something along the lines of, okay, P, couple of words, S, Paris, seen that word before, couple of connecty words, S, P-R-I-N-G, that's spring, Paris in the spring, got it. When we look at a sentence, we look at the whole sentence rather than the individual parts or the individual words in that sentence. So here's another one. You might have seen this picture too. Now that you've been primed to think about it, you might have actually caught this one, but that first line is what I if told you. Again, humans see what they want to see. If you look at that line, you're not going to say W-H-A-T, what, next word, I, next word, if. You're going to look at that whole thing, and you see the words what told you, a couple of connecty words, and you notice, okay, well, I've seen sentences like this before. This is almost certainly what if I told you. And most of the time, that quick process works just fine. But when you know about that process, you can switch words around and you can trick the brain. The next thing I'm going to show you is another one of these word processing tricks. This next one, I'm going to flash up a sentence, and for about 20 seconds or so, I'm going to leave the sentence up, and your job is to count every F that you see in this sentence. How many did you get? Most people can find 3 in that time. Some of us get 4. I've had one person get 5 once, but almost nobody gets all 6 of the F's that are in this sentence. When you're looking at this, you see finished files are the result of years of scientific experience. There's only 3 F noises in this sentence. But we also have 3 instances of the word of. But because the word of is said as if it was spelled O-V, you don't count those as F's unless you look at it very, very carefully. If you were a word processor and you hit Control F and found all the F's in the sentence, you'd find all 6 right away because a word processor doesn't make any difference between the F and the front of the word files or the F in the second letter of the word of. But our human brains don't consider the word of as a real word with F because it's spelled in our heads O-V, or we say it as if it was spelled O-V. So those are a couple of ways we can trick the brain by looking at sentences and changing what we're expecting from sentences, but our brains also use context, the context of the area around an image, to make sense of what we're looking at. You may have seen this image before. This is a famous illusion, but in the center we have 2 orange circles, and around the outside we have different contexts for both of those circles. So if you look at the circle on the left, it may look smaller because in relation to the context, those large blue circles on the outside, it seems a little bit smaller. And if you look at the one to the right, those small circles, it looks relatively larger compared to those circles. But these yellow circles in the middle, these orange circles in the middle, are actually the same exact size. But because we've changed the context, your brain parses or processes that information a little bit differently. So this is a pretty convincing illusion, but we can go one step further. You can take this illusion and you can make it dynamic. You can make this illusion move. So this is the center-focused illusion version of this illusion. When you're looking at this, you may be able to see that center circle getting smaller and larger and smaller and larger based off of its different contexts. So when the outside balls are small, then that ball in the center looks relatively larger, but when those are far away, the circles on the outside are far away and larger, the center might look relatively smaller. This is pretty convincing, but I've never run into anybody who's not convinced by this next illusion. Even though it's going to look like that center is changing, that center is staying the exact same size. But instead of focusing on the center, we're focusing on one of the outside rings. This is one of my favorite illusions because you can know exactly what's happening and your brain is still tricked by it. Even knowing exactly how this works, I'm still convinced that when the center circle is in the upper left, it's larger, and when it's in the lower right, it's smaller because of the changing contexts. For more information about contexts, we have this grid right here. This is a gradient from pure white to the left to pure black on the right. Now in the center, we have a square, and that square is the same color as the center line of this image. So what I'm going to do is I'm going to move this square off to the left and then off to the right. And I promise there's no video trickery here. I didn't change anything about this. All we're doing is sliding that square from the left to the right. When I first did this, you can print off a square like this and a gray square and slide it from one side to the other, and this illusion works in real life as well. But the first time I saw this, I didn't believe it. I thought it was video trickery. So to prove that it's not, I'm going to remove the background and do that same animation back and forth. And then we can go back and try it again. It really looks like it's changing colors because the context is changing. Here's the last one I'm going to show you on context. Those two checkerboards, A and B, those two checkerboard squares, are actually the same exact shade of gray. There are two things that are telling you they're different. One, if you look at the pattern of the checkerboards, you can see that there are dark gray checks and there are light gray checks. And if you look at where they are in the pattern, you should see that A is one of the dark grays and B is one of the light grays. But we have this added influence of B being in the shadow of that green cylinder. This is a very convincing illusion, and in order to convince myself that those two tiles are the same shade, I went ahead and edited out everything other than those two tiles. And when you do that, you're removing the context and you're removing all the information processing that's happening in the brain, and you're just looking at the two tiles themselves. When you look at just those two tiles themselves, you can see that they're actually the same shade. I'm going to flip back and forth between these a couple of times. It takes a while, but eventually you can convince yourself that those are the same shades. But when the context is back, I still see every time the B tile as being lighter than the A tile, even though you can figure out what's going on. So we've talked about word processing, we've talked a little bit about context, and next up I'm going to show you an image. And in this image, we have a couple of hazy colors around a central X. What I'm going to ask you to do is for about 10 seconds or so, just stare at that center X. Once you do this, for me, the colors start to fade away. And eventually you can convince yourself that you're looking at a gray square with a black cross in the middle of it. But those colors are still there, and then when you move your eye away from the cross, the colors suddenly reappear. So what's going on with this? We have another image that I'm going to put up that takes advantage of the same effect, but in this case it has some movement to it. This is a famous illusion called the Lilac Chaser, and move your eyes around the screen. Don't look at the crosshatch quite yet, but what you can see is if you follow the space, you can see that one of those lilac fuzzy circles on the outside is disappearing each time. Now go ahead and focus on that center X. And as you're doing this, the first thing you see is that that space turns from gray and now looks like a light lime green ball is going around. And if you keep staring at it, eventually that lime green ball seems to eat up all of the pink circles. And eventually, all you see is just that green ball going around and around and around. I'm going to leave this up for a second, but what you're seeing here is something called an afterimage. Your brain is doing a couple of things when you're looking at a scene. One of the things your brain is really tuned into is motion. And you can think about this way back in our evolutionary history. If you're looking at a scene and it's perfectly still, the chance that something dangerous is in that scene is small. But if you see a bush rustling or something like that, then your brain is tuned in to see that motion. So going back to this first image, when you're looking around the screen, you can look around the screen, sort of look at all the different corners, scroll through all the yellows or the purples. When your eyes are darting around this screen, the colors never disappear. The only time the colors disappear is when you stare fixedly at that center X. When you stare fixedly at that center X, your visual field is totally taken up by this, and there's no changing information. Your brain is doing something really interesting here. When there's no changing information, it tunes out any information that it sees so that it's easier to process. So if you're looking at something and it's not changing, your brain kind of views that as unimportant information and it processes it out. We have one more instance of an after effect. So what I'm going to put up is a colored image, and I'm going to ask you to look at this colored image for about 30 seconds. Again, I'm not going to jump anything out at you, but stare at that center dot and don't let your eyes wander around the image. Just stare at that single center dot in the middle. And what you're doing is you're looking at the image, and certain areas of this image are imprinting onto the back of your eyes, and your brain is getting used to this as what you're being able to see in your visual field. And I'm going to change the image in 3, 2, 1. You probably saw a color image there until your eyes moved around, and when your eyes moved around, the color immediately vanished. So I'm going to do this one more time. We're going to go back and look at this image, and what I'm going to ask you to do is stare at that central dot and don't move around the image at all with your eyes. See how long you can retain the color in the image. And if you look at it, it'll slowly fade back to black and white. In 3, 2, 1. The color slowly fades out as your brain starts processing the new information that it has. That effect is called an afterimage. And it not only works with color and with the Lilac Chasers or the colors, but it also works with motion. So now is the time where I'm going to put up it's a swirly image. Again, we're not going to scare you or anything. What I'm going to ask is that you stare at that center dot. We're not going to hypnotize you to do anything you wouldn't otherwise do, but stare at that center dot. And this motion is very repetitive. It's moving around and around and around. But your brain right now is working to cancel out that image. Because it's not changing, your brain is thinking, okay, this is stimuli that's not important to survival. So what's going to happen is eventually I'm going to change the image. And what I'm going to do is I'm going to change it to an image of trees. In 3, 2, 1. Looks like the trees are waving around in the wind. But as you look at this longer and longer, the trees slowly stop, and eventually all the motion is canceled out. So what was happening here? Your brain, seeing that image and seeing that motion, is trying to cancel that out because it's not changing. So what it's doing is it's basically changing your visual field to create sort of a counter motion. And when you change out of that frame of reference and you change into something like this picture, it's still trying to cancel out that same motion. I'm going to do this one more time. And if you're watching this with somebody, at the end of this 30 seconds, I'm going to ask you to look at their face. If you don't have somebody else or can't grab somebody else in the next couple seconds, try looking at the back of your hand after 30 seconds. So we're going to put this up. Resist the temptation to look early. Let your brain get nice and used to the motion by staring at that center dot. And then looking at either the back of your hand or someone else's face. Look in 3, 2, 1. Little bit weird, huh? So what's happening is your brain is trying to cancel out that motion, and you see motion in something that isn't moving that much, even though you know that that's not actually happening. But you perceive it and you see it. So this might be something that's happening with our Jedi mind trick. By understanding the brain so well, you might be able to figure out how to trick the brain. So we've got 2 Jedi mind tricks that you can do anytime. You can try these with your friends, you can try these with your parents. So the first one, I'm going to ask you a couple of math questions. I'm just going to ask you to go through these math questions as best you can, as quickly as you can, and then I'm going to ask a question at the end of it. Are you ready? And this may or may not have worked for you, but doing this in large groups of people, most people think of a carrot. Some people end up thinking of a tomato. But what your brain is doing there is it's processing the math that you're supposed to be doing, and when you're doing that, your brain is using up resources, and your brain is a little bit lazy. So when somebody asks you to name a vegetable and your brain is already working on these math problems, it finds the easiest thing that matches that criteria. When you think of a vegetable, most people don't go, kohlrabi. Most people think of something that's a more common, more quintessential vegetable. So most people think of carrot as the quintessential vegetable. Other people might think of a tomato, but you probably didn't think of anything too exotic because your brain was processing that information, and when you were asked to think of a vegetable, you think of the simplest possible vegetable. You can try this with lots of different things. Think of any category and think of what the quintessential thing is. Don't think too long, because the point is that it's the first thing you think of, and that will likely be a pretty good guess for when somebody says name a vegetable or name whatever your category is. They'll think of the simplest thing. So here's another one. If you want to win at rock, paper, scissors, there are people who've tried to figure this out. And one of the best strategies to win at rock, paper, scissors is to look someone in the eye, and as you're about to go, tell them, hey, by the way, I'm going to throw rock. The most common response to somebody thinking, okay, that person's going to throw rock, is that, they're trying to trick me. So they're not going to throw rock, they're going to throw something else. So thinking that you're trying to trick them, most often people will throw out scissors. And here's the trick. You tell them, I'm going to throw rock, and then you actually throw rock, then they're most likely to choose scissors, going one level deeper than you are, and because you were not trying to trick them and you were just telling them what you were going to do, then they end up winning. You end up winning. That ends up working about 50% of the time, which is better than totally random. And another thing is that most people will throw rock right off the bat, especially if they're trying to act tough. They'll throw rock more often. So if you want, you can try saying, I'm going to throw rock, and then actually throwing rock, expecting them to go one level deeper and throw scissors. Or if you don't want to do that, the best thing to try is to throw paper on the first chime, because more people throw rock for the first go of rock, paper, scissors than any other one. So those are some tips to helpfully win at rock, paper, scissors if you ever need to settle a dispute. So for this last part, I'm going to introduce you to something called the Stroop Test. And this has an at-home component. So I'm going to show you what the Stroop Test is, and I'm going to ask you some simple questions, and then I'm going to give it over to you, and I'm going to ask you to try to design your own Stroop tests. To start off, I'm going to ask you a couple of simple questions. For this first one, I just want you to say the word that you see on the screen as it pops up on the screen. Red, blue, green, orange. Next up, I'm going to ask you not to say the word that you see, but the color that the word is written in. Same challenge. So for that one, it would be black, 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 black. Even though the words were other colors, what I was asking was to say the color of the word, not the word itself. So we're going to try another iteration of this. Again, I'm asking for the color of the word, not the word itself. Red, blue, green, orange. Now in this last one, the color of the word matched the word itself. But this last one might prove a little trickier. Again, I'm asking for the color of the word, not the word itself. That got a little trickier. This effect is called the Stroop Test, and by showing you the color of the word rather than the word itself, and by making those different, so the word being blue, but the word being red, causes a little bit of cognitive dissonance. It causes a little bit of trouble in trying to say the color rather than the word. Every time you see this, you can't help but read the word. So asking the color requires another step of reading the word, ignoring the word, and then looking at the color and saying the color. So rather than one step of just reading it, there's a couple steps, and a lot of times people trip up on these. So you can try these yourself. You can make different variations of the Stroop test. We call it a distraction test. So this is one way of tricking the brain, like a Jedi might need to trick a stormtrooper. So to create your test, you can take pieces of paper, and I would recommend cutting them in half, because one piece of paper is a little big for this particular task, But you can cut these in half, and each half sheet of paper should have one word clearly written. That's the only real thing that you need to have for this. You can try different words. You can try words that are bold. You can try words that are really, really thin and see which one is easier. If you write the word red in blue ink with really, really bold, big letters, it might be easier than if you wrote the word blue with red ink using really, really skinny lines, because then it's harder to see the color itself. So you can experiment with that. You can also try words that have nothing to do with colors and see if that makes it easier. Or you can try making up nonsense words and seeing if that is easier to do the Stroop test with. You can try all different iterations, but one thing I would encourage is trying to figure out which ones are better than others. So you can make 4 or 5 and test them with different people, and you can also try timing your results or recording how many mistakes you make. You can have as much fun with this as you want. I've seen people who, instead of making solid lines, make dots. So they make a dotted line, and that's the word, and that might be harder or easier depending on how clearly you write your word. So this is a fun one. What you can try is you can also create these Stroop tests. Try testing your friends, try testing your parents, try testing your siblings, and if you have one that works really, really well, you can share that out with Science Discovery. So that's all I have for you today, and I'll leave you with these 3 questions. So, thank you very much. I've been Scott, and stay healthy.